A high-speed train is tearing across the landscape at nearly 300 kilometers per hour. Utility poles flash past. Fields collapse into streaks. Yet lift your eyes toward distant hills, and the world can look almost calm. Now compare that with a van moving at barely 100 kilometers per hour. The road rushes beneath you, nearby objects snap past the windows, and the whole vehicle may feel faster. That contrast has inspired a strange explanation. Perhaps certain vehicles use special glass that somehow makes the scenery appear slower. Some people even call it deceleration glass. But can a piece of glass really make 300 kilometers per hour look slow? To find out, forget the speedometer for a moment. The answer starts with the view. Let's get into it right here on Small Things. The myth of deceleration glass. The idea sounds believable because the experience behind it is real. Sit high in a bus or van at 100 kilometers per hour and the sensation can feel intense. Move into a low sedan traveling even faster and the same road may seem strangely relaxed. That contrast helped create a folk explanation. Better vehicles must be using glass that visually reduces speed. They are not. There is no glass that can make the outside world physically move more slowly. A windshield cannot change how fast a tree, road marking, or building passes the vehicle. So the strange part is not that people noticed a difference. They did. The mistake was blaming the glass. One distinction matters before we go further. The old deceleration glass idea comes from car and truck windshields. High-speed rail windows are a separate engineering problem. What connects them is the same misunderstanding. We often judge speed by what crosses our vision, then assume the transparent surface in front of us is somehow responsible. If the glass is innocent, what is creating the effect? Your eyes don't measure road speed directly. Your eyes do not carry a speedometer. One of the strongest clues they use is how quickly objects shift across your field of view. Distance can change that clue dramatically. Imagine a utility pole standing only a few meters from a railway line. As the train passes, the pole can cross the entire window and disappear almost instantly. Now look at a mountain several kilometers away. The train is still moving at exactly the same speed, but the mountain may stay in view for many seconds, barely changing position against the horizon. What changed was the angle through which each object moved in your vision. The same principle helps explain why extremely distant objects can appear almost stationary even when enormous motion is involved. The moon travels through space at tremendous speed, yet from Earth its position seems to change gradually because it is so far away. Speed alone does not determine how fast something looks. Distance can matter just as much. That is why scenery beside a high-speed railway can turn into a blur while distant terrain remains calm enough to study. At the same moment, your eyes can receive two completely different impressions of one train moving at one speed. And once you understand that, the odd difference between a van and a sedan becomes much easier to explain. Why a van can look faster from the driver's seat. A van or bus changes what fills your vision. The driver usually sits higher, the windshield is more upright, and the front of the vehicle is short enough that you can often see the road surprisingly close to the cabin. Lane markings, barriers, parked cars, and roadside objects enter your view nearby and disappear almost immediately. A sedan presents a different picture. You sit lower. The hood stretches farther ahead. The windshield is more steeply angled, and part of the road directly in front of the car is hidden. Your eyes are pushed toward scenery farther away. The van is not necessarily moving faster. It is simply giving your eyes more evidence of speed. The vehicle is changing the part of the world you are allowed to see. High-speed rail takes the same effect to an extreme. Look down beside the track and fences, poles and gravel collapse into streaks. Raise your eyes toward the horizon, and 300 kilometers per hour can suddenly look surprisingly peaceful. Perception explains why the speed can feel different, but it raises another question. If the window is not slowing the scenery, why does high-speed rail need such specialized glass at all? The glass doesn't slow the view, it cleans it up. A train window looks like empty space, but optically, it is another material that light must cross before reaching your eyes. No sheet of glass is perfectly invisible. Small variations in thickness, flatness, or material uniformity can bend light slightly differently across the surface. Straight features may appear warped. Objects can shift as your viewing angle changes. At high speed, when the scenery is already moving rapidly across the window, those small defects can add visual disturbance of their own. That is why high-speed rail glazing is made under tight optical tolerances. Thickness has to remain consistent. The surface has to stay flat. The material must be uniform enough that light passes through without obvious local changes in refraction. Its job is simple to describe and difficult to achieve. Pass the scene to your eyes without adding distortion of its own. Good rail glass makes the view cleaner and more faithful, while the train covers dozens of meters every second. That answers the optical side of the problem. The same pane, however, also sits between the passenger cabin and everything happening outside. At high speed, clarity is only part of what it has to deliver. A train window has to survive the journey. A high-speed rail window faces more than ordinary weather. When two fast trains pass each other in opposite directions, the pressure around their bodies changes sharply. That disturbance reaches the windows almost immediately, adding a sudden load to the glass. The glazing also has to cope with the possibility of impact from objects outside. So the window is being asked to do two very different jobs at once. Stay optically precise enough to see through while remaining mechanically strong enough to protect the cabin. And strength is only part of the safety story. Engineers also have to think about what happens if the glass is damaged badly enough to fail. Large, sharp fragments would create a second hazard inside the passenger compartment. Safety glazing is designed to control that breakage, reducing the danger from loose pieces while helping the inner barrier remain protective. Now the problem becomes more interesting. Make the pane tougher, and you have to process the glass. Process it poorly, and the same pane can develop stress, waviness, or distortion. Exactly the qualities passengers should not be looking through at high speed. The challenge is therefore unusually precise. Make a window strong enough to survive demanding service, while keeping it visually quiet enough that the passenger barely notices it. That is where manufacturing matters. How ordinary glass becomes high-speed glass. One important step is tempering. The glass enters a furnace and is heated to roughly 600 to 700 degrees Celsius. Reaching that temperature is only the beginning. The sheet has to heat as evenly as possible across both surfaces. If one region responds differently from another, the finished pane can develop uneven stress or surface waviness. That can affect mechanical consistency and degrade the optical quality the window needs. After heating, the glass is rapidly cooled in a controlled quenching process. This creates the internal stress pattern that gives tempered glass far greater strength than the original sheet and changes how it behaves when damaged. But tempering is not the finish line. The glass can then go through further procedures such as laminating and insulation before becoming part of the finished rail window. Each step adds another requirement to something that still has to look almost invisible from the passenger seat. That is the quiet contradiction behind the process. The window must be transformed enough to become stronger and safer, yet controlled carefully enough that the transformation does not ruin the view. By the time it reaches the train, all of that work should be difficult to notice, and that is exactly the point. Try this yourself. You can test the basic visual effect without a high-speed train. The next time you are a passenger in a car, bus, or train, pick two objects at once, one close to the vehicle and one far away. Watch the nearby object first. It will race across your vision and disappear. Then hold your eyes on the distant object. It may seem to drift slowly even though your vehicle has not changed speed at all. On another trip, compare the view from a high bus seat with the view from a low car seat. Notice how much of the nearby road you can see where the hood or dashboard blocks your view, and how quickly roadside objects cross the windshield. Nothing about the laws of motion has changed. You have simply changed the visual clues available to your eyes. That small experiment gives you the same answer hidden inside the high-speed train window. At 300 kilometers per hour, the scenery outside is moving exactly as fast as it always was. What changes is the visual evidence reaching you. Your eyes determine how fast the world looks. The glass determines how faithfully you see it. That is the real achievement of a high-speed train window. It has to stay flat and optically clean enough to disappear from your attention while remaining strong enough to handle the loads and hazards of high-speed travel. The most remarkable part is that when everything works, you hardly notice any of it. Next time you ride a high-speed train, look down at the track, then lift your eyes to the horizon. Which view makes 300 kilometers per hour feel real? Tell us below and subscribe to SST for more hidden stories behind the simplest things around us.